beamlines that was built along with the accelerator of the ALS. And we've gotten to the point with beamline instrumentation now that it actually made sense to pull out this beamline and replace it from scratch with all new equipment. This is a spectroscopy beamline, and spectroscopy is a general term for one of the main research methods that we use here. Spectroscopy basically means probing atomic bonds inside materials. And the X-rays that come out of the machine, or ultraviolet light, I'll just say X-rays to keep it simple, have enough energy that they can penetrate into materials and they can disturb the electrons that are involved in an atomic bond. One of two, roughly, things can happen. The photoelectric effect, which Einstein got a Nobel Prize for, the X-ray can hit that electron in the bond with enough energy that it ionizes it, kicks it completely out. You can then study the energy of that ionized electron and deduce something about the energy of the bond that you're trying to study. Or the electron can get excited to a higher energy shell and then cascade back down to its ground state, emitting photons as it goes. So that's sort of interesting because, think about it, we use electrons in the machine to create photons, to come down the beamline, to hit an electron, excite it, and then it creates photons, which we measure the energy of. So it's really kind of an interesting, self-referencing process, actually. So spectroscopy basically means that these guys can tune the energy of the incoming photons in various ways and look for resonances in what they're trying to study. And a resonance tells you, where a bond is happening. That's where it's resonance, right? You get an excitation right at that bond. And so they don't really take pictures. They take spectra building the experimental chamber that goes on the end. That's really where the beamline scientists can do their thing and know how to build these manipulators and load samples. And if you think about it, there's 10 to the minus 10, maybe a little worse than that vacuum in there. How do you actually take a sample from out here in the air and load it into that vacuum while maintaining the vacuum? The vacuum levels in our machines are good enough that if you were just to put a fingerprint on the inside of our machine, you would degrade our vacuum to the point where we would have to shut down for a couple weeks, clean it out, bake it, which means cook it to get all the stuff off the inside to get back to a good enough vacuum. So maintaining vacuum is huge here. So beamline in progress. One thing I can actually say, so you guys can kind of get the sense of the beamline. Here's a CAD drawing of it. This is the storage ring. So this is where the electrons are going around. It's one section of the storage ring. And then the beam of radiation is coming down, through all these manipulative optics into the chambers. One thing you might question is the beamline is quite long, actually. You can see where it comes out of the concrete shielding down there, and eventually there's going to be a chamber here. One reason these beamlines are long has to do, so these are X-ray microscopes, right? And in a microscope, you want to manipulate the light, just like a biology microscope. You want to focus it, move it around, throw away the energy you don't want, keep the energy you do want. The fact that X-rays are so high energy means that you can't use traditional optics. You can't use glass lenses because the X-rays absorb into the glass and get lost. So they have to play special tricks with optics. They use things called grazing incidence mirrors, where they'll have an extremely flat, we're talking like nanometer flat silicon or stainless steel or something surface, and the X-rays come in at a very shallow angle so that they don't have the penetrating vector into the material and bounce off at a very shallow angle. If you take that really flat surface and slightly bend it, you can create a parabolic mirror. So the X-rays coming in are actually focused as they go off. And then think about it, you have such a flat angle coming in and a flat angle going off, and you're trying to focus the beam. You need a lot of horizontal distance for that focus to actually resolve in anything meaningful. So that's why beamlines tend to be long. And we have beamlines where they're thinking about punching holes in the exterior wall and building a whole other room to make another beamline. So that's one thing about experiments. Here's one thing that's nice about these circular accelerators, though. You saw on the cartoon, there's room for tons of beamlines, right? 40 beamlines all circled around. Some of the newest accelerator light sources are linear accelerators. There's the LCLS down in Stanford you might have heard about. Those are optimized to be a little bit different, to create very, very short pulses of X-rays. And to do that, you can't make the electrons go in a circle because they tend to spread out and degrade that structure. So in a linear accelerator, it's great. You can do really exotic things, but you can only have 2 or 3 beamlines at the end just because of the space requirements. You can't bend the X-rays too much. Yeah.
How much energy does it lose once it hits like that stainless steel surface?
Ooh, that's probably, well, so it doesn't lose any energy. You lose X-rays. Some of them are absorbed. But the processes they use, it's refraction out of the material, right? So you're not like penetrating, getting slowed down, and then speeding up. You're actually refracting off the electric fields of the electrons that are in the bonds in that material and bending out that way. So you do lose brightness, you lose photons, but they maintain the same energy.